So the third talk in this session is from Andrea Bertozzi from UCLA. Please unplug this one.
Yeah, we need to just plug it in.
So Andrea has done as much as anybody to make Minority Report a real thing, I guess, with her crime prediction work.
Yeah, but that's not what I'm doing. We're having some screen issues here. This didn't happen before. Let's just... There we go. Thank you. I'm actually not going to speak about our work on crime, although this has a very loose connection, and some of those problems have motivated why we're looking at this. So I'm going to talk about diffuse interface models on graphs. This ties together some work that's been done, a large body of work that's been done using graph-based methods for classification of data. Ties it into some a well-known body of work in image processing using methods based on nonlinear partial differential equations. So the work is really on the boundary between these two areas, and what we've tried to do is unify some ideas from two different fields and put them together to come up with a new class of algorithms that we're kind of excited about. So the new work is joint with Arjuna Flenner, who's here, I think back in the back. There he is. Hi, Arjuna. But in order to explain the motivation, I really need to give some history of some of the recent work on diffuse interface PDE-based methods. So I'm going to start with that, because that's my background. My background is a nonlinear PDE rather than these sparse problems. So bear with me. I'm going to go through some of the background, and then I'm going to talk about the new stuff. And the earlier work was work with my students, some of my students and postdocs, Julia Dobrozhetskaya, Selim Isadoglu, Alan Gillette, and Carol Ashanlieb. Okay, so starting with the PDE-based problem, there's a beautiful connection between the total variation semi-norm, which is here, and what's called the Ginzburg-Landau functional, which is this one here. So the important point of the Ginzburg-Landau functional is that it has two terms. This is a double well. So W is typically segmenting your data into two components. It's a binary segmentation. This is a smooth double well potential that has two minima. So if you just minimize this, you're basically going to put U either into one of the two local minima. There are many ways you can do that, and the way you make the problem well posed is you add a regularization term. This is the classical one, which just says that yes, you can do that, but you also want the solution to have some degree of smoothness. This is the H1 semi-norm. So that introduces smoothness to the problem. Now notice there's an epsilon, and it's not written as epsilon for no reason, because it is indeed supposed to be a small parameter. And as we take epsilon very, very small, this metric starts to approximate this one here, especially in the case of binary data. And that's a theorem. That's a well-known result from calculus of variations. Okay, so how do we use this? Let's see. Oh, yeah, one thing let me just mention is that you can look at dynamics associated with either of these problems, and there's a lot of well-known results in the math literature for the sharp interface limit. So for example, if we take the gradient flow of the Ginzburg-Landau functional, we get the L2 gradient flow, we get the Allen-Kahn equation as epsilon goes to 0, we get motion by mean curvature, which is exactly what happens if you want to look at the first variation of the total of TV and then propagate. You would expect to get that. One can also look at different gradient structures. I won't go into this too much because it's not as relevant to what we're doing here, but I'll just say that you can do H-1 gradient flow. You get a Kahn-Hilliard model, which we have used for image processing applications, and it's important if you want to solve problems with multiple boundary conditions such as in-painting. Okay, so these models have appeared in the image processing literature in a number of contexts. I'll just quickly mention a lovely small paper by Selim Isadoglu on blind deconvolution of barcodes, which directly uses the Ginzburg-Landau functional in a variational setting. And also the classical Merriman-Benz-Osher scheme, which basically takes Allen-Kahn type dynamics and shows that you can solve for motion by mean curvature by separately solving the heat equation and then the threshold, which is basically like solving the gradient flow problem very fast for just the double well. And this has been generalized to image segmentation by Esadoglu and Tsai in 2006. So these ideas are not new to the PDE image processing literature. Here's another paper on in-painting with the Cahn-Hilliard model, which, since I have a relatively short amount of time, I think I'm not going to go into too many details here. Other than this, seems to work very well for a class of problems. We have transitioned it to NGA for road in-painting and to In-Qtel for document exploitation. And it can be done. So I guess the bottom line is, why would we want to continue working on these things for problems involving graphs? Well, for these specific PDE problems, these can be done very fast using a convex splitting, and I'll talk about that in the next slide. So this is important, the convex splitting. So in the case of PDEs, that first talk by Ingrid was lovely because she talked about the Fourier basis versus the wavelet basis, and that exact same idea comes up here. So if you happen to have a problem where say, for example here, this is sort of a hybrid gradient flow with two different metrics. The highest order term here is fourth order, which can be very expensive to compute the time evolution for. However, with a convex splitting scheme, we can make use of the fact that we have fast Fourier transform, which allows us to project this operator onto the Fourier basis, and it completely diagonalizes the operator. And once you diagonalize the operator, it's trivial to solve the problem. Okay, so that gives you fast schemes. Now there's a catch, because remember, we're not solving a linear problem. That would be easy. We're solving a nonlinear problem. We have the double well, and we also, in this case, we have a fidelity term, which is a characteristic function of some region. That also introduces an additional complication. It's a forcing term that we have to worry about. Okay, so now how do you make these algorithms fast? Here's one way to do it. This is convex splitting. So these are very non-convex functionals that we're trying to minimize. So what you do is you take your convex functional and you write it as the difference between or the sum of, say, of a convex and a concave part. Now there are many ways, this is not unique, this decomposition. There are many ways you can do it. The trick is to do it in such a way so that when you look at the gradient, this is a discrete approximation of a gradient descent. Okay, with the time step delta t, and the catch is that you do the new time level for the convex part and the old time level for the concave part. Now you want to set this up with a specific decomposition so that two things are true. One is that you can do the new time level, so there's an implicit solve you have to do here for the new time level, obviously, because it's an equation for the solution at the new time level. So you want to be able to do that very fast. Like, for example, can you take this and immediately project onto some eigenspace, and then you're done. So that's one thing you want to be able to do. The second thing is you want this decomposition to be such that the splitting is at least either unconditionally stable or very weakly conditionally stable, meaning you can take a bigger delta t. So that's the rough idea. And then, with some work, you can, in a recent paper with Carola, we proved that these class of schemes for a bunch of in-painting methods are either unconditionally stable or very weakly conditionally stable, and we proved convergence. Okay, so now, so this idea works very well for PDEs, and it's been used not only in imaging, but a lot of other contexts as well, this convex splitting. It's not, it's a well-known method. So now what we can do is we can take these ideas and we can generalize them to wavelet bases. So this is a modification of the Ginzburg-Landau functional. This was part of my student Julia's PhD thesis work, her recent thesis work. So the idea is, rather than working with the classical differential Ginzburg-Landau functional, we make a note that the Laplace operator, which comes from the first variation of this term, this is our regularizing term. Our Laplace operator, as Ingrid very nicely pointed out in her first talk, you can always write this Laplace operator, you can decompose it into the eigenfunctions and eigenvalues, where the eigenfunctions are just the Fourier basis. So we have that fact. And so when we look at this, we realize that this may not be the right basis for the problems we're interested in. We might want to work with a basis that localizes the features of interest in the image better. So we have lots of wonderful wavelet bases we can work with. So why not redefine this operator? So we're not going to work with this operator, we're going to throw it out, but we're going to replace it with something that's almost exactly the same in some sense. So in what sense do I mean? Well, we're going to define the operator by its eigenfunctions and eigenvalues. So here it is. So we pick a wavelet basis, and then we pick the eigenvalue. So we pick the wavelet basis to be the eigenfunctions of the operator, and then the eigenvalues are going to scale precisely like the Laplacian eigenvalue scale, meaning that if you take any particular wavelet, it has an obvious spatial scale associated with it. Okay, so then that's a length scale. You take 1 over that length squared, and that's the eigenvalue, and there it is right there. Okay, so this gives you a very well-defined operator. It has very similar scaling properties to the Laplace operator. What it doesn't have is rotational invariance. But nevertheless, it has some lovely properties, and you can use it for the same kinds of objectives that one would use the Ginzburg-Landau functional. So here's an example with blind deconvolution of a 2D barcode. In this case, we have a choice of wavelet bases, and obviously for this one, the Haar basis is a really good choice because it exactly decomposes our barcode. So we can do very well with, this is a noisy, blurry data, and this is the recovered barcode. We get perfect recovery for this very noisy, blurry data. Here's another example. Within painting, it works quite well. And actually, Julie in her thesis even went to the trouble of looking at the epsilon to 0 limit for her wavelet Ginzburg-Landau functional. So this is the classical Ginzburg-Landau functional. This is Julia's functional. Let me mention that the big difference is really this first term, and you can actually rewrite this into a Besov semi-norm. So this is there's well-known analysis here. So what one gets so one can actually look at the epsilon to 0 limit, and one actually can prove that in the epsilon to 0 limit we actually get, rather than the TV functional, we get a Wolf shape energy. So it's close to TV, but you get facets. So the punchline is, rather than having energy minimizers that are, say, perfect circles in the case of the total variation semi-norm, we get Wolf shapes like this. They have facets. Basically, the idea is that there are preferred directions of edges. Slightly preferred directions of edges. Okay, so all of this is previous work. This one just appeared this year in Interfaces and Free Boundaries. So now graphs. How do we take these ideas and make them work on graphs? And this is joint work with Arjuna Flenner. This is it's a paper's on my website. It's submitted for publication. This picture is a teaser. We actually did not use this data. This is a network of gang rivalries in the city of Los Angeles, and we have some interest in using this for some of the social network data that we have, but we haven't applied it to the gangs yet, although hopefully we will. So now imagine that you have a graph, and there are weights on a graph. It's a weighted graph, and so in our case, we looked at typically at weights that had this kind of structure. So every node on the graph has some data associated with it. There's data supported on the graph, and then you have some metric to compare the data at different nodes, and then we take the weight just to be an exponential function like this with some scaling parameter tau. What's nice about this is that you can apply it to problems that are very much not images, a much broader class of problems. So I think this is very timely. We have one example, which is looking at some of the voting records of the US Congress. Can we classify, for example, if we don't know their party affiliation, can we look at their votes and figure out which party they're in? And maybe in this year that would be a trivial exercise. However, in some of the historical data, it's a little harder to do. Okay, so another thing we can do is we can revisit this lovely method from image processing called non-local means, which is also essentially a graph-based method, and we have a new way of solving that problem, or something like that problem. Okay, so how do we do this? Well, we want to construct a graph-based Ginzburg-Landau functional. So we want to construct something like the Ginzburg-Landau functional, only using some object associated with the graph. And the natural object to look at, of course, is the graph Laplacian, because that is essentially the object that we've looked at for these other classes. We've got the classical differential Laplace operator, the classical differential Laplace operator. We've defined a wavelet-based version of that operator, and that's worked quite well. So it's very natural to look at the graph Laplacian, not only for those reasons, but also because there's a huge body of literature on the graph Laplacian, and we can build on that. Okay, so there are various ways one can define the graph Laplacian. This is the simplest construction one can do, where we have this. So we have nodes on the graph. We can look at the weight associated with the different nodes on the graph, connecting one node to another node, and then we have the degree associated with each node. And then one can construct an inner product, so that this shouldn't be new to many of you here. One can construct an inner product based on that Laplace operator. One can scale the Laplace operator in different ways. This is the symmetric scaling that we like. It's worked pretty well for our algorithm, so we've chosen this symmetric scaling. And then at the end of the day, we can actually write down an energy functional that's basically a version of our Ginzburg-Landau functional plus a fidelity term here. So these two terms here are the graph-based Ginzburg-Landau functional. So we have the first term, which is our regularizing term with a small parameter epsilon, plus we have our double well, okay? So those are the two terms, and then we have this. So this is an example where we have say we're going to do some classification, and we have some known data. So this would give us the known data, which would presumably be a fairly small subset of the data we'd like to classify. Okay, so now if, just a short soundbite on the proper normalization of the graph Laplacian. So Arjuna did some calculations and noticed that if we just took this is an example with a couple of cows, and this is using basically the non-local means form of the weights. So what we're doing here is we're looking at patch neighborhoods, meaning that we take every pixel in the image and we take another pixel in the image and we look at a local patch around each of those pixels, and that patch actually defines the vector associated with the pixel. And then you take those two vectors and you can construct weights of this type here, where there's a comparison. This inside inner product would be a comparison between the patch neighborhoods. Okay, so you take that and then you construct the graph Laplacian, and depending on how you scale it, you may find some lovely leading order eigenvectors, or you may find stuff that's picking up, more or less few edges and noise in the image. So we've chosen the scaling that gives us the images on the right. Okay, so now suppose you have a very high dimensional problem like this. And this, by the way, this is not a sparse problem. We connect every point on the image to every other point on the image, so that's huge. And it's not sparse. Nevertheless, if we want to be able to do a fairly fast decomposition of the graph Laplacian into eigenfunctions and eigenvalues, there are good algorithms out there. We've tried this one, the Nystrom extension, which comes from, I guess, about 7 years ago. This is a very well-known paper on the Nystrom extension. I won't go into details on that other than it's out there. There's a lot of literature on this. And by the way, you don't have to use, to use our method, you don't need to use specifically Nystrom. Any method that you have out there to do a spectral decomposition will work. Moreover, if you have an algorithm that doesn't explicitly do spectral decomposition, but rather solves some version of the graph Poisson equation, then we can use that too. So either, if you have any tool out there that does any of these things, you can basically plug and play them into our method. Okay. So in this particular case, where we happen to have a fast way to compute eigenfunctions and eigenvalues, then this is the full convex splitting method for the Ginzburg-Landau graph problem. Okay, so it's pretty cheap. I mean, we can go through the steps here, but basically the steps involve projections of things onto these eigenfunctions that are known. So first of all, you have to compute the eigenfunctions and eigenvalues, although, like I said, there are other ways to do this. So if you have a fast way to do that. Oh, and also let me mention that we don't actually use every single eigenfunction. So for example, in this very expensive problem with the cows, where you connect every point to every other point, we certainly don't use the entire spectrum and the entire set of eigenfunctions. That would be very expensive. Rather, what we do is we identify the important ones for the problem, and then we only project onto those, and we basically ignore the other ones. Okay, so that's another. So in some sense, so even though I say that's not a sparse problem, in some sense it is, in the sense that we're selecting a very small, relatively small subset of eigenfunctions and eigenvectors to project onto. Okay, so basically once you have those, these projections are very fast. Here's the initial data projected, it's cube projected. We need the cube because of the fact that, that we have this extra term in the minimization, which involves the first variation of the double well potential, and the cube comes from the double well potential. So that's the nonlinearity introduced to the problem right there. These are just, this is all just algebra. And then this is the actual time step right here. This is computing the solution on the next time step. These are the coefficients of the solution projected onto the eigenfunctions of the Laplacian on the next time step. And then we basically repeat. We do these projections again, and we just repeat, repeat, repeat. And you do this for some number of iterations until you get the answer. So now, the proof is in the pudding. How does it work? So we tried this on a number of examples, only one of which was an image example. So the first is the two moons. This is data embedded in R100. It's a classical test problem for these kinds of methods. And you can see that the data kind of wraps around each other. These are projections into R2. So there's noise that gives us additional projections into all these other dimensions. And so the classical second eigenfunction calculation doesn't do very well in this problem because of the complicated geometry. And here's the Ginzburg-Landau solution, and of course that does well, or I wouldn't be showing you the picture. But more importantly, let's look at not only performance but also speed in comparison to some recent methods. So here's 2 Laplacian, which is very, very fast. So this is time and this is accuracy. So the 2 Laplacian is very fast because it's just an eigenvalue calculation. However, it's not very accurate, as you can see here. So these are very recent 1 Laplacian methods. This is from a paper of Hein and Buehler. And the 1 Laplacian methods do quite well in terms of accuracy, but they're a little more computational. They take more time than our method. So this is the timing run. Ours is faster than these two, and it actually is a little bit better in terms of accuracy as well. Okay, here's the U.S. Congress. This is voting records from 1984. We have 435 members of the House of Representatives. We want to classify their party. If we want to assume we don't know their party affiliation, suppose they're secret, they don't tell you what party they're in, but you see how they vote. So what we do is we pre-identify, so we have 5 where we know the ground truth of their party affiliation. That's a small number. It's on the order of 1%. And then we want to try to figure out the remaining 430, given that, of course, for this data, we actually do have ground truth for all of them. And we look at, based on the number of votes we're using for the data set, how well do we do? So with 16 votes, we get 96% correct, which is pretty good. For 8 votes, we don't do quite as well, but you can see as we increase the number of votes, we do better and better. And again, this is historical data. We haven't tried this on data from the last year or two. It would be interesting. Okay, so here's the cows. So for this example, what we're trying to do is, this is a machine learning example. So we're given this is our learning, this is the learning data. So for this data set, the user goes in and hand identifies the cows, but rather poorly. So you can see that this hand identification has included a bit of the grass as well. This would be like a user just going in and manually tracing out the cows. Then we want the computer to automatically find the cows in another image. So we don't give it any information other than here's the image. For this data set, because of the high dimensionality and the connectivity of the graph, we did use the Nystrom extension on this. We did not use it on these prior examples, mainly because well, this was fairly low dimensional. We can use sort of standard linear algebra routines. This one, in order to compare it with the Hein and Buehler method, where they do sparsify the problem, we sparsified it in exactly the same way to do a fair comparison with their method. Although we didn't have to. We could have kept it fully connected. So for the cows, it's fully connected. We use Nystrom, and this runs very fast. It does quite a good job of classification. So it picks out the right. There are a few stray pixels, but it picks out the cows quite well in the unknown image. And this runs, I don't know, I would say on a minute or two, Arjuna, on your MacBook. Is that right? Less than a minute. He says it runs in less than a minute on his laptop, on his MacBook Pro laptop. So that's pretty fast. So let me mention that in terms of making the method fast, there are things we've done, but a lot of things we haven't done. So for example, we're doing a basic gradient flow here with a fixed time step. We haven't tried adaptive time stepping. Typically when you solve these kinds of nonlinear PDEs, you can get a speed up of anywhere from a factor of 5 to a factor of 20 using adaptive time stepping, and we haven't even done that for this method. One can do, we've picked sort of out of the box a good method for the spectral decomposition, but there are a lot of good methods out there. Some of you may have better methods than the one we're using. So there are a lot of ways one could make this even faster, but given what we've done so far, it seems to be performing very well. It seems kind of interesting, and I think in particular, it would be very interesting to look at some of the possible theoretical connections between things like the one-Laplacian method and our method, because we're not directly solving the same problem, but given the well-known PDE literature connecting things like TV to Ginsburg-Landau, it would be interesting to try to understand that theoretical connection as well. So I think I'll stop there since I'm right exactly at the end of my time. Thank you. That's great. Morrow says it would be interesting to compare this with other diffusion models where you change this time scale diffusion at the point. I agree. I mean, there's a huge literature out there on diffusion models, and there are lots of potentially very interesting math problems that are out there to connect these, not only in terms of algorithm design, but just in terms of the theory. I think there's a lot of good stuff out there. Yes. I'm sorry. You want to know about the cows and I didn't hear the full. What features were used to obtain the segmentation? Is that the question? Okay. So I'm still not sure I know exactly. So let me just tell you what we did. And Arjuna, correct me, yell if I say this wrong, because Arjuna wrote the code for this, so he knows better than I do. But so what we're doing is, to obtain the segmentation for the cows, what we do is we construct a graph Laplacian, which is based on the data. It's based on this data and this data. So we take both of these data sets. So given the known data, so there's known data and there's a known segmentation, which is not so good. Okay, and then there's unknown data, but to compute the graph Laplacian, we use both the known data and the unknown data. So we construct a graph that involves, so the graph, all the nodes in the graph are all the pixels in this image and all the pixels in this image. Then we construct a weight associated, so given any node, and any other node, we need to construct a weight associated with those two nodes. So the way we do it is we take a local patch around the first pixel, a local patch around the second pixel, and notice that the first and second pixels could be in the same image, they could be in two different images, they could be in this image together. So it's just a whole collection of pixels. So we take local patches and we do comparisons between the local patches, and there are a number of metrics that you can use for that, but basically what you do, you think of it as an array around that pixel, and you have another array around the other pixel, and that's like a big vector, okay? And then you can, so in terms of how do you compare the actual colors and so forth, there are a number of ways you can do that. You can do a straight L2, you can do spectral angle, so there are a lot of different things you can do in terms of the details of how you treat the colors. But in terms of the basic construction of the graph, that's how we do it. And then what we do is we use that graph Laplacian, we basically plug that into this. Let me show you the formula, this. So the LS is that graph, is the symmetric graph Laplacian, right, plugged in right there. And then this piece over here says, hey, I know some of the pixels belong in the cow, in this one image. So that gives us this term here, where the lambdas is basically forcing it to be classified a certain way. Like basically this is an in or out classification, it's binary. So this lambda is going to say you're in if you happen to be in this cow that we know. Okay, so that's it. And so then we minimize this, and we minimize it using gradient descent, and we do it using the specific convex splitting algorithm that I just talked about. And also, by the way, let me mention that the convex splitting algorithm combined with gradient descent is actually equivalent to another well-known sort of convex splitting method that doesn't involve gradient descent explicitly, but it's in the optimization literature. So we didn't actually have to use gradient descent. In case you're wondering, why do we do it? Just I'm a PDE person, so for me it's convenient to write it that way, and it makes sense. And also we can then tie it into well-known adaptive time-stepping methods too, if we wanted to do that, which would be sort of like a parameter estimation method for the general optimization problem. Yeah, Mauro. Oh, that's a great question. Yeah, absolutely. Maura wants to know what's the relationship between epsilon and the number of eigenvectors that you need. Excellent question. I can answer that precisely in the case of the Fourier basis. And for this problem, I think it's still, we're just trying to figure it out, but let me explain it in terms of the Fourier basis, because that's very precise. So epsilon is a diffuse interface scale, and if we go back to the classical PDE problem, I don't think I have a good picture to show you, but yeah, this one is okay, I guess. So basically what it's doing is it gives you a small scale on which these interfaces are no longer sharp. They actually become diffuse. It defines precisely that scale. So if you're using it it's actually a downfall. If you're using it in an image processing application, it means that numerically you have to resolve that epsilon scale. That's actually why we went to wavelets in the first place, because the wavelets are localized and they help that. They really help that issue. Okay, so again, this epsilon is also going to play. It's going to play the role of a scale, but now it's a scale involving the graph. It's a scale involving diffusions on the graph. And like I say, this is a new method, so there's a lot of open problems just sort of sitting there, and that's